Hey, good morning, guys. Let's do a quick audio and visual check. Make sure you can hear me and see me. If you can hear me and see me, give me a thumbs up or just say we got you in the chat box. Okay, cool. Very good. Hey, so hope you guys are doing good today. Today is Thursday. We have 29 classwork. So this one and then 30, and then guys, we are done. And then we go into our review for the exam on May 12th. So this one is going to be a little bit lengthy. I'll try to make it as quick as possible, but there's some pretty important details in here. Riemann sums, and we'll kind of get to all those and what they are. So hopefully it's not too long. Yeah, I see what you're saying. Yeah, the packet's pretty long. So a lot of reading, though. A lot of knowledge here, and a little bit of practice. So we'll kind of get right into it. But hope you guys are doing well. Hey, check out Timmy's devotion video today. They sent it out on email, so check that out for chapel. Timmy did a good job. I'm not sure if you're here with us now, but if you watch it later, you did a good job, man. But before we go to the 29 classwork, are there any questions over the homework? Any questions over the homework from the night before? 28 homework. Any questions over any of this? 28, the accumulation function homework. Okay, yeah. Hey, great question. Number 2, don't worry about number 2. I'm sorry. I didn't know that was on there, but that's basically what we're going to do today, okay? The answer is 15 calls. I don't know if you tried to figure it out logically or what you did, but we'll actually talk about today. That has to do with the trapezoidal rule. I don't know why it's on here, but for some reason it snuck on there, so don't worry about number 2. You'll know how to do that at the end of the day today, okay? You'll know how to do that here in just a second. Sorry about that. I should have looked on there and saw it, but I guess it just kind of slipped through. So, all right. Any other questions on number 28, the accumulation function? I actually found this right here to be like finding the area of this top portion right up here. I don't know. I'm not sure how. If you guys might have known how to do that. If you did, props to you. Any other questions from Morgan, Carter, or Ben? If you're not, give me a thumbs up if you're good. Again, I'll show you 1 and 2. Sorry about that. So there's A. Kind of scroll through the answers here. There's the graph from backside. There's our graph. Does having the answers help? Like having that answer key, does that help you a little bit? Oh, wrong thing. There it is. Just kind of going through the answers here. I don't know where the answer key, I don't know if you all saw in J that the answer key included 3 and 4. It said it was the steepest decline, but 3 and 4, between days 3 and 4 wasn't a decline, it was an incline. So that's what I think there was just an error on the answer key there, and then day 4 and 9. So All right. So that is that. If you have any questions, feel free. You can hit me up later. So, you three, I think we have three in here. Give me a thumbs up if you are good to go. You meaning you have this out, you're ready to go. All right, so here we go. This is Riemann sums. So we can find definite integrals if we view the graph of the function that is made up of straight lines and or quarter or semicircles. But if we are given a function f of x in algebraic form and we wish to find the definite integral from a, b, f of x dx, we need a procedure. We start by approximating the area by using rectangular regions. Below, you are given a curve, f of x on 0 to 4. That should be a comma there. Estimate what you believe the definite integral from 0 to 4 f of x dx is. Then, on the next three graphs, draw 2 rectangles, 4 rectangles, 8 rectangles, total the areas and sum them for another estimate of the total area under the curve. All right, so let's look at this first one. Let's look at these first three. Let me minimize me out of the way a little bit. Okay, so looking at this very first one right here, guys, we want to somewhat calculate the area. Now, I know it's kind of hard to see on the, let me adjust this camera a little bit, guys. I know it's kind of hard to see on the graph, but it's going up by ones here. So this is 5, 10, and 15. Okay. So, and of course, this down here is going by 0. So 0, 1, 2, 3, and 4. So one of you guys just shoot in an approximation of what you might think the area of this underneath this curve would be right here. What would the area of this curve right under here be? Just shoot me a guess, just an estimation of what you might think it is. Kind of think of it like this, guys. Kind of think if this was a right triangle, it would be, a 4 by like 18. A little bit more than 5, Ben. Because think each square is 5. Or yeah, each square would be a 5. A 1 by 5 would be a 5. Yeah, that's it. It's by 5, yeah. It's the y-axis going up by would be going up by 5s. It's a bit confusing. Okay, so Morgan says 36, 29. Okay, so even if you were just thinking about this graph, think about the right triangle. What if we said it was like a 4 by 15? And we know it goes up a little bit more than 15. But what if it was a 4 by 15? 4 times 15 is 60. And then half of 60, 1/2 base times height. The base is 4, the height is 15. Or excuse me, 15. That'd be about 60. So then half of that's 30. But we're not using quite all of that, right? So I'm going to go with an approximation of like 25. Or an estimate. Approximate, or my estimation would be like 25. Okay? Now let's calculate the area of these two rectangles right here. Okay? So keep in mind that is 5, 10, 15. So this first one is and that's a 1 right there, and that's 2, and that's 3, and that's 4. So the first one is a 2 by 5, which is 10. Plus this 2 by, let's just call that 18 up there. It's a little past 15, so it looks like it's getting close to 20, so 18. So then, oh no, it'd be 2 times 18, sorry. 2 times 18 would be, or double 18 would be 36. So then that would put us at 38, or excuse me, 46. My math's way off today. And of course, you all would know that we're losing, I mean, a lot of that's taking up that space there, okay? So that's doing it with 2 rectangles. Now if we go to 4 rectangles, and guys, don't, our goal here is just to figure out the area under the curve, okay? And this is kind of the process of the route in which we could do it. So, going to this one right here, that has an area of, I know it's hard to see, but that'd be a 2 right there. 2 by 1 would be 2, plus that is a 1 by 5, so that would be 5. So that one's 2, that one's 5. That would be a 1 by 10, so that's 10. And that one right there, we said that was like 18 a while ago, so we can kind of stick with 18. It might be 17. Again, it's just approximation. So plus 18. So then that would be 35. But then if we took it to 8 rectangles, okay? If we went 8 rectangles, and again, each one of this, that's like area 1 and area 2. This would be area 1, area 2, area 3, area 4. And those correlate to what we have down here. You know, A1, A2, A3, A4. Okay? So here I'd have 8 areas. A1, A2, A3, A4, A5, A6, A7, and A8. Okay? Those are my areas. So that first one, it is going, okay, yeah, so if we're keeping the thing that this is 5 and this is 1, so that would be like 0.5, I guess that would be 0.5, and let's just assume it's going up 2. So this right here would be 0.5, and then let's just say that's 2. So that would be an area of 1. So A1 has an area of 1. Plus area 2 would go up, it's going up by a half. And let's say that it's at, well, no, sorry. If that's 0.5, let's say that's 1. I'm sorry. So that first A1 is 0.5. And then this would be 2. So a 2 by a half would be 1. Yeah, now I'm on the right track. Sorry. And then the next one, and the next one would go up to 3, so then that would be 1.5. And again, I'm just trying to, that's A1, that's A2, that's A3. And I'm saying that's still a half times 3. So half of 3 is 1.5. Half of 5 would be 2.5. Half of 7, let's just call that 7, it's kind of hard to read, would be 3.5. Half of A6, which would be 10, would be 5, plus half of 13, A7 would be 6.5, and then half of A8, we'll just call that 18, would be 9. So if we were to add all that up, we would get 29 and a half. So a little sloppy in there, just trying to find out those measurements. The graph is not the best looking graph, okay? So that's kind of our understanding of it, and really that may be like 17 there. So that may be like 8.5. So we could call it just 29 even. Okay? So we got 29, we got 35 using 4 rectangles, we got 46 using 2 rectangles, and 25 just approximating it with our own eye. Okay? Now again, the goal of this is to somehow figure out the total area underneath the curve. So the function in the problem above is actually x squared plus 1. So let us estimate the area is equal to the definite integral from 0 to 4 x squared plus 1 dx using 2, 4, 8 rectangles using analytical methods rather than graphical approach. Okay, so instead of using like the graphs, let's just look at it based on more of the analytical or algebraic type way. So we know the area of the 2 rectangles we know the total area is going to be equal to the area of the first triangle plus the area of the second triangle. So we could really say then here, and we could break that down and say the area of A1 is the base times the height of the first one. From the height one, because obviously the going to be 2 different heights here, and then plus the base of height 2. So again, this is doing it like this. Now let's do it the more algebraic way. So A is equal to the base times height 1 plus base times height 2. Well, notice here we can factor out of B. So our area is equal to the base times the height of the 1 plus the height of the second. All right, so then from there, let's identify what the height would be, okay? The height of this, of the 2 rectangles, okay, the height of this would just simply be f of 2, okay? So base times the height of f of 2, and then plus the height of h of f of 4, which is this height. Okay, so again, the height of the first rectangle is just literally whatever f of 2 is, the y coordinate of f of 2. Okay, and then the height of the second one is whatever the last number is, which is 4 here. It's the height of that one. Okay, so then we could just plug f of 2 into our equation here. F of 2, 2 squared plus 1 is 5. So A is equal to, and then we know our base of the base of the rectangle is 2 here. Okay, the base of the rectangle is 2. So we say 2 times f of 2 would be 5 plus f of 4. 4 squared is 16. 16 plus 1 is 17. That would be 22 times 2 is equal to 44. So our number might have been a little off right here. That may be, again, that could be at 17. Like I said down there, that could be at 17, and that's why those numbers aren't necessarily matching. But if we made this up here 17, then that would make that 34, which would make that 44. So that probably is a little bit more reality there. So that number up there probably is 17. Which would make that 17, which would make that 34. So, all right. Then we do the same thing with 4 rectangles. The area of 4 rectangles is equal to the area of the first one plus the area of the second one plus the area of the third one plus the area of the fourth one. And we know that the area then would be equal to the base times the height of the first plus the base times height of the second one plus the base times height of the third one plus the base times height of the fourth one. Then, of course, we could factor a b out of all that and get b times the quantity of height 1 plus height 2 plus the height of the third plus the height of the fourth. Then from there, a would be equal to the height of the first one would be at whatever point that was. Okay? So wherever the first one ends, so that's at 1. So the height of the first one would be f of 1. Height of the second one would be f of 2. Height of the third one would be f of 3. Height of the last one would be f of 4. Okay? And an easy way to do that is to determine your distance right here of your definite integral and then just divide it by how many rectangles you have. So if your distance is 4, you divide the distance by 4, and that tells you each base of each rectangle will be 1. So the base times f of 1 plus f of 2 plus f of 3 plus f of 4. Notice the same thing worked over here. We had 2 rectangles. Our distance was 4. Just divide it by 2, and that would tell you your base is for those 2. So then we have area is equal to our base. Our base in this case is just simply 1. F of 1, now we're just plugging these into this. So 1 squared plus 1 is 2. 2 squared plus 1 is 5. 3 squared plus 1 is 10. 4 squared is 17. And that takes us to 17 and 17 is 34. So it matches what we got up there. Once we fixed our little, we didn't know what that unit was, but now we know it's 17. All right, then we'll do an abbreviated version of 8 rectangles because as you can imagine, this would get pretty crazy. So the area is equal to area of 1 plus area of 2 plus ... plus area of 3, or excuse me, area of 8. So then therefore the area is equal to the base height of the first one plus the base height of the second one plus ... the base height of the 8th one. Then of course I can factor b out. B times the height of the first plus the height of the second plus the height of the 8th. Now, to determine, keep in mind, my distance that I'm going is from 0 to 4, and if I have 8 rectangles from 0 to 4, 4 divided by 8 is 1/2, okay? So each base is going to be 1/2, and then I just need to take my heights by 1/2 as well. So area is equal to B, and then that would be like F of 0.5 plus F of 1 dot, and excuse me, I should put some dots there. And I'm going to say plus ... F of, and I should end at 4 if I'm going up by 1's 8 times. That then will give me area equals the base, which is 0.5, and then I just calculate all of that right there. And we could go through there. It's 1.5 plus 2 plus 3.25 plus 5 plus 7.25 plus 10 plus 13.25 plus 17. So, and then that actually gives us a total of 29.5. So really close with what we had there. something. We may have had a point off or something. Okay. So, and if you don't have your calculator today, I'd go ahead and get that out because this is going to be a pretty heavy calculator lesson. All right. So if you don't have that, if you don't mind, go ahead and get that out. So as you go through this process, several things should be apparent to you. Drawing the function in rectangles are not really necessary. We don't have to actually draw the rectangles. We can just kind of do the math like we did here. And something else, the more rectangles you create, the more work you have to do. A lot of arithmetic, a lot of adding, okay? The more rectangles you create, the smaller the error in calculating the area for each rectangle is, though. As the number of rectangles approach infinity, the error for each, in the error meaning the, what we're off by, the error for each rectangle approaches too. So the more rectangles you could get in there, the closer your area is going to get. And if you have an infinite number of errors, each approaching 0, the total error should approach 0. All right. And if you have no area, you have the if you have no error, you have the true area. Now I may say error really weird. That maybe that Kentucky coming out of me. So area is equal to the limit as the number of rectangles approaches infinity, and that big E sigma just simply means the sum of the area of the first, and that is equal to, and these are all the same, basically the same thing. They're all saying the same thing within that. Okay? So as you're representing your rectangles approaching infinity, you're getting closer to your truer error. Excuse me, your truer or your true area. Error and area close together. That don't do well with me. Okay? All right, give me a thumbs up if you're kind of with me, maybe a little bit with me. Okay? Morgan's with me. Ben's with me. Okay, cool. So, I know you're still here, Carter. I hope you're with me as in terms of kind of seeing this a little bit. So, as a common example, if f of x equals 4x plus 12 minus x squared, our goal is to find the definite integral 1 to 5 f of x dx, which is basically, it wants us to find the area of the function from 1 to 5. As shown in the figure to the right. It wants us to find this area. We will have 4 techniques, 4 approximation techniques that will allow us to do this. The first 3 are called the Riemann Sums, named after the German mathematician Bernhard Riemann, 1826 to 1866. That's actually very sad that he lived such a short life. But Riemann Sums will find the sum of the area of rectangles. Okay, so we will create 4 rectangles of equal bases in our examples. Since we are interested in the area from x equals 1 to x equals 5, and there are 4 rectangles, the base of each rectangle is luckily 1. Such a simple value for the base won't always occur, so in general, let's call the base b. Let us define x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4, the locations on the x-axis where we build our rectangle's heights. In this case, x sub 0 is 1. X sub 0 is 1. Has a height of 1. X sub 0 has a height of 1. X sub 1 has a height of 2. X sub 2 has a height of 3. Okay, this may be, unless their pictures is just totally off. Maybe this is referring possibly more to this. So, x sub 3 has a height of 4. Okay, no, it's not talking about like where it's hidden. It's talking about the actual triangle. So x sub 1 is, yeah, that's really confusing within that. So maybe it's referring more to this one. Okay. For this specific example, f of x equals 4x plus 12 minus x squared. Okay, yeah, these are different examples, I assume. All right. So let's talk about the left Riemann sums. So our general case is just as we did in the beginning. The base of the height of 0 plus the base of the first, this height, plus the base of this height, plus the base of the second height, plus the base of the third height. You factor your b out, and the area of a left Riemann sums, and we'll refer to this as LRS, is equal to this. Okay? And since the height of 8, and since h sub I is equal to f of x sub I, this becomes just basically what we did on the front. A little bit different formatting there. So it becomes basically f of 1, f of 2, yada, yada, yada. Okay? Giving us this area of 58. So this is a lot of information, and it's maybe even harder to explain over the internet. But here's what you need to know, okay? When you do the left Riemann sums, your rectangles, your height of your rectangles is at the leftmost point of the rectangle. Notice this right here. Here, 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 and here. Okay? That's where it is hitting. That's where the rectangle is hitting it. Okay? So here's what I want you to kind of notice in this. You're not calculating this height right here. Sorry about the blur. You're not calculating this height right here, which would be x4, or the height would be the h4. Notice h4 is not on here. It's just h0, h1, h2, h3, but h4 is not on there. Okay? And the reason that is because this is the left Riemann sums. We're calculating the area based on the rectangles on the left side. All right? Now, jump down here to right Riemann sums. Right Riemann sums, RRS. Okay? Notice this. This is doing the right side of the rectangle. So same curve here, guys. Same curve, but the left calculates it on the left hand side of the rectangle. The right calculates it on the right hand side. So as you can see, there's a difference in some area here. This has some overhang. This has some under. This has some stuff under the curve that's not there. Okay? But here's what I want you to know the difference is this right here. And I think if you can get this, you should be pretty good. That the area of a LRS does not include the rightmost point. Does not include the rightmost point. And with the and with the RRS, notice it doesn't include the leftmost point. Now, let's look at kind of this right here, okay? So the height of h sub 0, h sub 1, h sub 2, h sub 3. So when we're saying h sub 0, we're talking about from here to here. The height of 1 would be from here to here. Height of 2 would be from x2 up to here. And then height 3 would be here to here. So watch this. So my base is 1, okay? The distance from 1 to 5. The distance from 1 to 5 is 4. And if I have 4 rectangles, then my base, each base of the rectangle is 1, okay? So my area is equal to my base, which is 1. Then f of 1. What is f of 1? F of 1, right here, would simply be 15. So that's 15 there. Okay? That next one, f of 2, would be, the second height there, would be 16. And then the next one, 15. And then the next one, 13. So when you add all that up together, you're saying 15 times 1, 16 times the height of 16 times 1, the height of 15 times 1, the height of 13 times 1. And all of that's just going to be 15, 16, 15, and 13, which gives us an area of 58. And that's using the left Riemann sums. Now using the right Riemann sums, notice the difference here. Notice that we didn't include f of 5 here. We didn't include f of 5, so that's 1.2, 3, 4, 5. We didn't include the fifth point. But notice down here on the right Riemann sums, we do not include f of 1. We don't include that very first point. We're just going on the right-hand side. And we do include the f of 5 here. So I'm really wanting you to see that's the biggest difference between LRS and RRS, is that the left-hand side, you don't include the furthest right point. The right-hand side, you don't include the leftmost point. Everything else is pretty standard. So again, the base is still 1, f of 2 is 16, f of 3 is 15, f of 4 is 12, and f of 5 here would be 7, giving us a total of 50. So, now, although these numbers are 8 numbers apart, keep in mind that they're just approximations using two kind of different points or values, okay? And you may be wondering, well, which one do you want us to use? Well, it could ask you, use the left Riemann sums to find the area, and it would be looking for that number, okay? And, of course, again, your graph would be more specific, so we would know, the exact points, okay? Same thing down here with this one. If it said, calculate the area of, if it said, find the definite integral from 1 to 5 f of x, and that's f of x, and it gave you the graph, it would give you better points, or you could calculate it just based on using the function, okay? Hope you're seeing the difference between LRS and RRS. So, left Riemann sums, LRS, builds rectangles starting with the leftmost x value. Right Riemann sums, RRS, builds rectangles ending with the rightmost x value. They both use the exact same rectangles except from the leftmost and the rightmost. So, if a function is increasing on an interval, a right Riemann sum will over-approximate the area, while a left Riemann sum will under-approximate an interval. For a function decreasing on an interval, a left Riemann sum will over-approximate the area, while the right sum will under-approximate it. So, notice this was decreasing, okay? So the left, LRS, overshot it. What over-approximate? They over-approximated here and under-approximated here. Those were the words I was looking for earlier. I couldn't think of them. So if it's decreasing, left Riemann sums will over-approximate it. Decreasing right Riemann sums will under-approximate it. So, examples. For the following functions, calculate the right Riemann sum and left Riemann sum on the given interval and number of rectangles. Okay. You guys ready for this? Not too crazy, but just kind of getting going here. Give me a thumbs up. You still with me? You're kind of seeing it a little bit. Thank you, Morgan. All right, cool, Ben. So we're going to calculate both the RRS and the LRS sum on the given intervals. All right, so here's what I need to determine first right here is my base here. All right, so my distance is from 3 to 5, which is 2. So another way you can kind of think about this is just say base, and the base is equal, it's basically just saying 5 minus 3, and then just put that over 4, how many rectangles we have. So the distance is 2, and then 2 over 4 would be 1/2. So again, guys, thinking about this as a, thinking about this on a graph, if I was going from 3 to 5, and I had 4 rectangles going, 1, 2, 3, 4, each base is 1/2. So my base is 1/2. Okay? Again, 1/2, 1/2, 1/2, 1/2. From 3 to 5, with 4 rectangles would be a base each of 1/2. All right? Now let's start with LRS first. Let's start with left Riemann sum first. All right? So, here's what we are going to say. The area is equal to the base, right? Now, again, I'm pulling this from the beginning, all right? Right here, area is equal to base times the height of the first one, the height of the second one, yada, yada, yada. Okay? So, you should be able to see A equals base. Let me just actually write that out. So area is equal to base. I don't want to just jump in and you're like, whoa, where'd we go with that? Area equals base of the, I don't want to write this, f of x sub 0 plus f of x sub 1. And really, whatever it is going to be based on how many there are, okay? So our area here is equal to our base, which is 1/2 times, now here's what you need to think about. The height of the first one, okay, would just simply be where you're starting at the leftmost. Okay, that's your right, but to the leftmost point. So that would just simply be f of 3. Okay, so f of 3 plus, now each one goes up, each rectangle goes up by 1/2. So plus f of 3.5 plus f of 4 plus f of 4.5. Now notice here, f of 5, which is this endpoint over here, that would be to the right. It's not on there because we're calculating it on the left. Give me a thumbs up if you're understanding this. Okay? It's basically, these are just basically like the height of the first one, the height of the 0 plus the height of the first one. That's what that's basically meaning there. Give me a thumbs up that we're kind of clear on this. Cool, Morgan. Very good. All right, so now we just plug this into our function to see what's working here. Area is equal to 1/2 f of 3 times 3 plus 2 would be 11. Plus 3.5 times 3 plus 2 would be 12.5. Plus 14 plus 15.5. And that, guys, is equal to 26.5. And not the sum of that, but when you add all that up and multiply it by half, you get 26.5. Okay. Obviously, we could do that on the calculator, so just going ahead and just shooting that to you. Now, RRS, same thing, area of my base, but this time I don't do the height of the first one, I go height of the next one plus h of 2 dot dot dot, and I would go till I got to the end, which would be h of whatever it may be, h of 5 or whatever. Okay, so that's just, I'm just trying to use that as an example so you see where I'm getting the f of stuff. So the area is equal to, the base is still 1/2, but we're not going to start at 3, the leftmost point. We start at the next one, which is f of 3.5, because that's going, now we're on the right hand side of the the rectangle. Plus f of 4 plus f of 4.5 plus f of 5. So notice the difference again, guys. This is why I said I think the key in knowing Riemann's left and right Riemann sum. This does not this doesn't include the rightmost point. This does not include the leftmost point. So from there we got a is equal to, we've already calculated a bunch of this, 1/2 times 12.5 plus 14 plus 15.5, and then that would be just plus 17. You add all that up, multiply it times 1/2, and you should get 29.5. Now, notice this would be an increasing function. That's increasing, right? 3x plus 2 is just going up like that. So it's increasing. So notice, when something is increasing, the right-hand side overestimates it. The left-hand side underestimates it. Okay? All right. Jumping over here to number 2. So we need to do LRS and RRS. So let's identify our base. So the distance we're going, we would just say 1 minus 0. And we just put that over 4. How many rectangles we have here? So the distance is 1 basically. And there's 4 rectangles. So we basically have each base is 1/4. All right. So let's look at LRS. LRS would be A equals 1/4 times, now this is where our F comes in. It starts at 0, so F of 0. And then the next left-hand side would be at 0.25, so plus f of 0.25 plus f of 0.5 plus f of 0.75, and then I would be F. It's getting a little sloppy over there. Sorry, can't even see it. So f of 0, f of 0.25, f of 0.5, f of 0.75. That's my 4 left-hand side of my rectangles, and I don't put 1 because it's the left-hand side. Now, to save us some time, I went ahead and did some of these calculations. Obviously, that first one's pretty simple. That would be 9 plus 0.25 squared times 4, and then 9 minus that would be 8.75. Plus 0.5 would be 8, and 0.75 would be 6.75. If you add all of this up, multiply it times 1/4 in your calculator, you should get it to be about 8.125. And guys, I have these equal signs, but they're really approximate, right? This is not the true one because we're basing it on just a few number of, so always do these as approximate. Sorry, I get into a bad habit. So always make sure you make it approximate. All right, now let's jump to RRS. RRS, the area, would be 1/4, but we don't include the leftmost point because now we're on the right-hand side. So we say f of 0.25 plus f of 0.5 plus f of 0.75 plus f of 1. Okay, from there, since I knew this would, we'd use a calculator for this. If you wouldn't have to have a calculator for this, but if you, obviously, it'll save us some time. So area is equal to 1/4, and then that would be 8.75 plus 8 plus 6.75 plus 5. And then you add that together, multiply it times 1/4, we get 7.125. And again, with that being negative 4x, that parabola is doing this. It's going upside down, so it's decreasing. So right-hand side underestimates, left-hand side overestimates. Rarely will you need to use many rectangles to approximate areas on the AP exam, but using the calculator list feature will allow you to find the area under a curve to extreme accuracy using a large numbers of rectangles. Suppose you want to approximate the area under f of x equals 12 minus x squared on 1 to 2 using 8 rectangles. Okay, so again, 1 to 2 using 8 rectangles. That is not an inordinately large number of rectangles, but plugging intermediate x values into the function will be messy arithmetic, and accuracy is important. So the base of each rectangle, your distance divided by the number of rectangles, 2 minus 1/8, is 1/8, which is 0.125. So if we use left Riemann sums, we need to find f of 1, f of 1.125, f of 1.25, f of 1, on and on until all the way till we get to 1.875. We put the numbers into our list. You can either type them in or use the sequence. So give me a thumbs up if you have your calculator. Give me a thumbs up if you have your calculator. All right, cool. So, now, of course, we know that we're going to something else, but, obviously you're going to have access to a calculator. So if you were to be asked questions like this, hey, you never know. And this is a really simple way to kind of do it. Especially, I think everybody in here is taking stats, so you're pretty good with like lists and stuff like that, or I assume you are. So what we want to do here, okay, is we want to kind of go through this problem. All right. So our first thing we want to do is we're going to type them into the list. Now, of course, you all know that you can go to list and edit and type these in hand by hand, 1.25, okay? Or I assume you would know that you can use the sequence command under list, second list, and then go to ops, and then it's 5 here, sequence. Again, that's second list or second stat, go over to ops and hit sequence 5, and then this will allow us to type it in. Now yours is probably blank, mine is filled in with what it should be, x, 1. So my expression is x, my variable is x. I start at 1, I end at 1.875, and I step 0.125 each time because that is 1/8. And then from there, I just simply hit paste. And of course, I want to paste it in 1. Okay. So if I go through that again, second list, ops, sequence, and go down here to paste. And then I need to hit what? Stat edit. And then I want to paste it right here. All right, been a minute since I've done it, I guess. Ops, 5, sequence. I want to paste. Yeah, there we go. Sorry, you got to go there first and then hit it. And then that punches it all in. Go to your list first. Don't be at the home screen. That was my error that I made. Okay, so look, if I was to clear that out and do it all over again, second stat, I'm at my home screen, okay, I would go here to, I would go to stat or second stat, ops, I would go to sequence, I would type in, it's always going to be x and x, I'm starting at 1, okay, I start at 1 because this is going from 1 to 2, so I start at 1, but I'm doing the LRS, so I'm not going all the way to 2, and I'm stepping up by 0.125 each time, 1/8 each time. All right? And then I just, once I got that down, okay, I have that sequence down. If I hit paste here, that's what I did the first time, and it took me there, which is not, that's not where you want to be, but you want to be at stat edit, and then go to, that's where you want to then go to your sequence at. And that's just going to second stat and then going to ops and then going to sequence and then pasting it there and that. You all probably know this a little bit better than I do. Okay. Now I've messed it up. Oh, okay. Hey, I know what it is, Morgan. Sorry, Ben and Morgan. All right, so I was typing it in wrong. Okay. So all right, so I'm starting from the beginning one more time. Okay. So I want to be in list. Okay. And once I'm in the list, I hit edit the first list. I'm right here. Okay. I'm right here. Now, where you need to be, because if you keep getting error, you need to be up 1, okay? Because what we're doing, if you're doing that, you're typing in that whole sequence to that, but we need to put the sequence to the very top one. So watch this. If I do it right here and I hit, second list and go over to ops and hit sequence, and then all my sequence is there correctly, but when I hit paste, it gives me an error right here because I'm not in the right spot. So I probably hit go to and just hit go up one, or I guess you can hit quit, but then go back into it, edit your list, and make sure you're at the very top of it. And then go second stat ops sequence and then paste it. Make with that at the top, and that's when it goes in. Okay? Is that making sense now? All right. Trial and error with the calculator. Okay, so then from there, what we'd want to do is you'd want to have your function in y1. So go to y1, make sure we have our function there. Ben, you good? All right, cool, Ben. Make sure you have your function there, 12 minus x squared in y1. And then once you have that in there, okay, you want to define list 2 as y1, L1, okay? So go back to our list, which is just hitting stat, edit that, and then go over to list 2 and be at the top. And what you want it to say is y1, L1 down there. So how you get y1 is by going to vars, yvars function. So vars is right here to the left of clear. Vars, yvars, function, y1. And then to find your list, you go second list and then just type in list 1. And let's put that in parentheses. So second list, list 1. Let's put that in parentheses like that. I'm not sure if it matters or not, but we'll put it there. Give me a thumbs up if you guys have that. Cool. So then from there, we would just hit enter. And there we go. That is all the, that's exactly what we need. Okay? That is the area of each triangle of the function, okay, under each rectangle for LRS. So now what we just need to do, okay, is just simply go back to the home screen, hit second quit, and we want to go to the sum portion of it. So go second list, which is second stat, go over to math, and we want to find the sum of L2. So second list, L2. All right. So that's the sum of all the, that would be the sum of all that. And then we divide that by 8 to get our 8.41, which would be the sum of the left-hand side. Thumbs up when you guys get that. All right, cool. Cool, guys. All right. Now, to find your right-hand side, so to compute the right Riemann sum, we can use the fact that we need to have f of 1.125 to 2 in list 1. But most is already there. We just need to replace the first one with the last one, which is 2. All right? Now, the list 2 will not automatically recompute, but we can easily find f of 2, which is 6, okay? But I'll show you how kind of I would do it. So again, let's go back to our list and edit. So this is based on the left-hand side, but keep in mind the left-hand side does not use 1 here. Okay, it doesn't use 1, it uses 2. So I just delete both of those, and those come up. And I literally just went up there and hit delete, and it deleted both of those. And then down here, I just need to add 2. Okay, now look, it didn't automatically compute that. But what I'm just going to do, I know it's 6. But what I'm going to do, you could type in 6 down there. But what I do is I'm just going to simply clear that. And then I'm just going to redo it by saying what I said up here, the whole Y1, L1. So vars, function, Y1, second list, L1. And I did something wrong. Sorry. Vars, Y-vars, function, put in parentheses, and then we just need to say list 1. There you go. Sorry about that. I don't know what I typed wrong, but I typed something. And I know that's 6, and like I said, and like the notes say, we could just type in 6 here, but just to be sure, you could just do that again. And then we just do the same thing, okay? We do the same thing, sum of L2 now, which is the right-hand side. So second, quit, we go second, stat, math, sum, which is 5. And we're going to do the sum of list 2, second list, 2. And we just divide it by 8 to get 7.914. Okay? Luckily, this is on video, so you see my error. So you can like go back and not fix yours. But we got both the answers that the notes have, so that shows that we're doing it right. Okay? So if you were ever to get A, this is just an easy way to use your calculator to find the area under a curve if you're given the function. Okay? Pretty simple. Does this make sense to you guys? Give me a thumbs up. Cool, Morgan. Cool, Ben. I don't know who else we have with us. I don't know if Carter dipped or just didn't have his calculator or what. All right. So that's just a way to do that. Feel free to rewatch that to kind of go through, maybe use another problem. Maybe a problem that we do. Okay. So that's the first 2. Now we have 2 more. As Carter said, this was pretty big packet here. So the next one we do will be the midpoint. Midpoint Riemann sums have the advantage of having every rectangle very close to the true area because it over approximates the area on one side and under approximates it on the other side. However, the computation for midpoint rectangles frequently is messier than the left and right Riemann sums. We go back to our example finding the area under 4x plus 12 minus x squared using the midpoint Riemann sum of 4 rectangles. Okay? So this is our midpoint Riemann sums. And the difference is here, guys, is we're taking the midpoint now. So we're not on the left-hand side, we're not on the right-hand side, we're in the middle of those 4 rectangles. So, in order to find that, okay, in order to find the middle of anything is to take the average. So what we do is, again, kind of follow this along right here. So the base, it's always area equals the base, whatever our base is here, okay, which here our base is just simply 1, okay. But then what we're going to do is we're going to say x sub 0, this point plus this point divided by 2 to get the middle. Then we go to the next one. This point plus this point divided by 2 to get the middle. Then we go to this point divided by 2 to get the middle. This point to this point divided by 2 to get the middle. Okay? And that's what all of that is right there. And as the notes say, that's a bit messy. All right. But if we were to look at this specifically, so again, we would just need to find f of 1.5, f of 2.5, f of 3.5, f of 4.5. All right. When you type that into your case up there, which here we have the function, so it's pretty simple, you would just type those in, get that, and we're looking at 27.5. And that's a little bit closer, okay? That's a little bit, you may say a little bit better. But like it says, the computation is a little bit messy. So that's the third rule. Our fourth rule is method of approximating the areas called the Trapezoidal Rule. That was that question number 2, Morgan, on the homework. So it is based on creating trapezoids and not rectangles. It is a superior method of approximation because the curves use diagonal lines along the curve rather than horizontal lines used by Riemann sums. The area of a trapezoid, as shown in figure to the right, is A equals 1/2 base times the height of 1 plus the height of 2. So as you see here, the trapezoidal rule looks so much better, okay? We're not missing too much, not overestimating too much, not underestimating too much, because these are simply trapezoids here, opposed to just doing big rectangles. And that should make sense if you remember what we talked about. I don't know when it was, but we talked about how guardrails, they seem to curve, right? They seem to curve, but really they're just straight lines, okay? Really they're just straight guardrails because the state are the ones that often put those in, and while they look like a curve, they're really just straight lines because bending that metal could be very expensive, all right? So here is the thing with, here's the general case for this, okay? It's the area of the first one, so it's just basically doing base over 2, okay? Base over 2, whatever the base is over 2, times literally the base and the height of this is just base times height of the first one, okay? And then plus b over 2 times the second one, the third one, the fourth one. Now, this works perfectly, okay, when your bases are even, okay? So I want you to look at this specific case right here. So notice we say base over 2 times, now this is what's a little bit different. Your first point, okay, your very first point is just going to be f of 1. Okay? It's just going to be f of 1. Whatever that may be. And your very last point would be f of 5. Okay? But everything else in between, how many ever numbers that is for you, or for whatever it'll be basically f of that number times 2. Okay? F of that number times 2. So, if we were looking at this one, okay, so it's saying the first one, x sub 0, or f of 1, f of 1 is 15. So f of 1 is 15, plus we say 2 times f of 2. 2 times f of 2, which is right here, which would be 16. That's 15. F of 3, which would be 15, and we say 2 times 15, f of this one, which would be 12, and then we just say plus 7 here. Okay? So that's the key piece there. With LRS and RRS, the key is that, LRS, you don't use the rightmost point. RRS, you don't use the leftmost point. The key with trapezoidal rule is that you start with your first one and your last one are going to be there, but then you multiply all the middle by 2. All your middle f ofs by 2. All right? So, it can be easily shown that the trapezoidal sum is the average of the left and right Riemann sums. In summary, we have 4 methods of approximating the area under a curve. So basically what we're saying there, sorry, I kind of read through that fast. Basically, this sum is basically just the average of the left and right Riemann sums. If you were to think about going back to the beginning, if we went back to those problems that we did right here, think about this. If we did the left, if this right here, this is a positive slope, so this is underestimating it, this is overestimating it. If we found the average of that, that would be basically the trapezoidal rule, okay? But you don't got to do all that work. You can just simply multiply those, okay? Now, you may be saying, well, why are we multiplying it times 2? This may help you see that. Why do we multiply the middle by 2? Notice here, there's just one f of 3, and there's only one f of 5. But notice there's 2 f of 3.5s, 2 f of 4s, and 2 f of 4.5s. So that 2 is just basically coming from doing this. It's the average of this, putting these two together. But notice how each one of these has 2, but the ends are not. So it's just basically putting all that together. Okay? So, 4 formulas, guys. 4 methods of approximating area under a curve of f of x from 1x to a number of x using n portions, rectangles, or trapezoids, assuming that f of x is greater than 0. And that the rectangles / trapezoids all have the same base b. The base b is calculated, b equals the distance over n. Okay? So that's our LRS, RRS, midpoint formula, or not midpoint formula, but midpoint of the area, and then the trapezoid. Okay? Okay, let's jump to the back. So, and of course it would give us a trig one to start with, all right? So if you have a unit circle, grab that unit circle. So, approximate the area under the definite integral 0 to 5 pi over 6 sine x dx using 5 left and right Riemann sums. Verify that using the trapezoidal rule for 5 trapezoids is the average of LRS and RRS. Okay. So we start with LRS. All right, let's just start with LRS. So LRS, and we may have to write a little small here because it's probably going to take a little bit of work here. So let's start with LRS. Now, we of course need to know our base, okay? Our base is our distance divided by how many rectangles we have. So it's from 0 to 5 pi over 6. So basically 5 pi over 6 minus 0 over 5 rectangles. Okay? So that would look like this actually. 5 pi over 6 divided by 5 over 1. Keep it, change it, flip it, and then our 5s would cancel. So that means our base is pi over 6. So our LRS, A is approximately our base, pi over 6. Okay, and then again, when we're using the left, we want to include 0, but not 5 pi over 6. So we say f of 0, okay, and then plus f of, again, each one is going up by pi over 6, okay? Each one is going up by pi over 6. So f of 0 plus f pi of 6, pi over 6, plus, now you may be saying, well, how do I get this next one? Well, just say pi over 6 plus pi over 6, and that would give you 2 pi over 6, which is pi over 3. Okay, so then that's f of pi over 3 plus, and then just add it to that again. Add pi over 6 to that. Well, in order to get that to 6, you'd have to multiply it by 2, so that'd be 2 pi plus pi over 6, which would take us to 3 pi over 6, which is a half. Okay, so 1/2 pi, or pi over 2, plus f of pi over 2. And then your next one, if you kept adding it, you would get, if you add another pi over 6 here, that'd be 4 pi over 6. And 4 pi over 6 is 2/3 plus f of 2 pi over 3. Now, if you were to add one more, that would change that to 5 pi over 6. Think about if I add another pi over 6 here, change that to 6, which make that 4. 4 plus pi is is 5 pi over 6. And you don't want to go to 5 pi over 6 because that's the end. So we stop here. And then we just calculate this using our function, which is sine. So sine of 0. So a is approximately pi over 6. Sine of 0 is 0. Sine of pi over 6, the y-coordinate of pi over 6 is a half, plus the y-coordinate of pi over 3 is radical 3 over 2, plus sine of pi over 2 would be 1. That's 90 degrees, right? And then sine of 2 pi over 3 would be radical 3 over 2. Now this gets a little messy, okay? It gets a little messy. So that equals, okay, 1/2 and 1 is 3/2, okay? 1/2 and 1 is 1.5 or 3/2, okay? So I can write that as 3, but I know that that has a denominator of 2 as well, or actually I need to put my pi over 6. Pi over 6 times 3, and then I can say plus 2 radical 3. There's 2 radical 3's here, so 2 radical 3 over 2. But since 3 is over 2, you guys know I can just put that over 2. And again, I could separate that, and that would be 3/2 plus 2 over radical 3 over 2. But after I do that, that would just lead me to this. Pi times 3 plus 2 radical 3 over 12. When I multiply 6 times 2 and get that to be 12. And that's what I'm looking for there. So that's the LRS. Now let's go RRS. And we say A is approximately, so same thing here, but we're not using 0 and we use the other one. So pi over 6. So we start with f of pi over 6. F of pi over 6 plus f of pi over 3 plus f of pi over 2 plus f of 2 pi over 3 plus f of 5 pi over 6. Okay, then we go through there and say A is approximately pi over 6. Now we've already calculated a ton of this. So we got 1/2 plus radical 3 over 2 plus 1 plus radical 3 over 2. That's the first 4. And then 5 pi over 6 would be 1/2. Sine of 5 pi over 6 would be 1/2. Okay, same thing here, guys. 1/2 plus 1 plus 1/2 is 2. All right. But I want to kind of keep this simple because I just want to multiply 6 times the denominator. So this would be approximately pi over 6 times. Now I know that 1/2 plus 1 plus 1/2 is 2. So I could write this out as 2 plus, oh man. I need to send those in. Sorry, I just got a crazy email. So I know I could write this as 2 plus 2 radical 3 over 2. But to make it simple, I'll just say 4 plus 2 radical 3 over 2. And the reason I do that, guys, is because of this right here. Is because if I'm looking at this, 4 over 2, I know that's 2, and that's how I got that, and that. Okay? But if I put it like this, then I can just multiply that. So then that would be equal to pi times 4 plus 2 radical 3 over 12. Okay? So now go trapezoid rule. Okay? Trapezoid. So the trapezoid rule, and I'm just going to follow the trapezoid rule, which was basically back here. Okay? Base over 2 is equal to the first one, but then I'm just going to multiply the second ones by 2. So it's going to look just like these. It's going to look just like this, but it's also going to have both ends, but each one in the middle is going to have a 2 on it. So it's going to look probably a little sloppy right here. So the area is equal to 1/2 the base, or b over 2, which my base here is pi over 6, times f of 0. So always start with f of 0. Always start with that endpoint, plus 2 times f of pi over 6, plus, I'm going to have to go horizontal with this, guys, plus 2 f of pi over 3, plus 2f pi over 2, plus 2f 2 pi over 3, and then plus just that last endpoint, which would be plus f of 5 pi over 6. Now I'm going to say area is equal to, now that right there would be pi over 12. And then let's go ahead and calculate all that. Well, we basically have it all already. F of 0 is 0. Plus 2 times pi over 6, which would just basically be all of this right here, but we can cancel the 0. So plus 1, and then plus radical 3, plus 2, because 2 times 1. So f of 0 is 0. F of 2 times f of pi over 6 is 1/2, but when you multiply it times 2, it cancels. So just want to make sure you see where I'm coming with that. Plus the last one, 2 pi over 3, was radical 3 over 2, but when you multiply it times 2, you just get radical 3. And then from there, you would get, and then the last one would just be 1/2. So area is equal to, area right here would then be equal to, once we add all that up, 0, 1, 3 and a half, So that would be pi over 2 times 7/2, which is 3.5, plus 2 radical 3. There's 2 radical 3's there. Now, since all this right here is, since this is under 2, let's put that under 2. But in order to do that, we'd have to multiply this right here times 2 in order to get that to be 4. And that's actually 12, not 2. So then our final would look like pi over 12 times 7 plus 4 radical 3 over 2. And then that would equal my final answer of pi times 7 plus 4 radical 3 all over 24, or over 24, because 12 times 2. Okay. Now, what we need to do with our calculator, guys, is to do this. Is we need to calculate this right here. Okay? And we need to show that these two, okay, is the same as that. Now, if you guys are fine with me, because we've already been here for an hour and 40 minutes, just trust me that they are the same. Is that cool? If you will just trust me that those are the same, instead of like, which it wouldn't take long to type in, but you know, just typing them in, showing you those, that the sum of those two is equal to that. Okay, can we trust me on that? Give me a thumbs up. You're still with me? Okay, cool. And I typed it in my calculator earlier today, and it was all there. Okay, so that's a lot to kind of take in, but when you take this and add it to this, it will equal that right there. All right, so you might wonder, why under a curve, why is the area under a curve so important? If the x-axis is measured in x units and the y-axis is measured in y units, the area under the curve is measured in xy units. Okay? So if the x-axis is measured in feet and the y-axis is measured in feet, the area is measured in feet squared. If the x-axis is measured in hours and the y-axis is measured in miles per hour, then the hours would cancel out and the area is used in miles. X-axis is measured in hours and the y-axis is measured in miles per hour squared, then the area would be miles per hour. So just a kind of an example of where this kind of makes a little sense. So a traffic light turns red and the driver stops the car in 5 seconds. Over those 5 seconds, the speed in feet per second are recorded. The graph to the right plots those points with straight lines joining them. Find the area under the curve using a trapezoidal rule with 5 trapezoids. Interpret the answer and explain why this is an approximation. Okay, so first thing we know, we need to know our base for the trapezoid. So what's our base? Our base for the trapezoid, with 5 trapezoids coming here, our distance is from 0 to 5, guys. So therefore our base would be 1. If our distance right here, if we're trying to find the area of all this curve right here, then the distance we're going is from 0 to 5. And with 5 trapezoids, that would make each base have a base of 1. All right? So then you just need to know that area of a trapezoid formula. It's the base over 2. So our base is 1, so it's 1 over 2, and then it's each point but all the middle points are double, okay? Because it's taking that average of the it's taking basically the both of those left and right Riemann sums, okay? So A is equal to 1/2 times, now we start at f of 0, and it's just by itself. But then we go plus 2f of 1. And then plus 2f of 2. Plus 2f of 3. Plus 2f of 4. And then just plus f of 5. The ends are by themselves. Now, luckily for us, we don't have to we can see the graph, but it also gave us a table so we can kind of interpret what those are. Okay, so area is equal to 1/2 f of 0. When it's at 0 at time seconds, the speed is 88. So 88 plus f of 1 is at 60, and then times 2 would be 120. So f of 1. And again, you could look right here and even determine that that's 60, and then you just multiply it times 2. Plus f of 2, when x is 2, y is 40. So 40 times 2 is 80. Plus f of 3 is 25, times that 2 is 50. Plus f of 4 is, I think, 10. Yeah, 10. So we multiply it times 2, and that's 20. And then f of 5 is 0. So then we say area is equal to 1/2. And if you add all of that up, you get some number. I don't know what it is, but I can just tell you this, that the area is equal to 179. Okay? Now watch this. The area is the, like we set up here, it's the XY unit. So the X unit is seconds. It's seconds. And then the other one is the Y unit is feet per second. So it's second, feet per second. So what those units do is the seconds cancel out, and that gives us 179 feet. So basically it says explain why this is, interpret the answer. So the interpretation of the answer would just be in 5 seconds, it takes the car to stop. In 5 seconds, it takes the car. Let me rephrase it. It takes 179 feet for the car to stop. Sorry, bad wording there. In 5 seconds, it takes 179 feet for the car to stop. Now, you may say, explain why this is just an approximation. Well, one, we don't know the speed at times between the given ones, okay? So we really don't know that speed in the times between those given amounts. So we really don't know, where it was or how fast the brakes were slammed. Like, for instance, could have been going faster and then stopped and then kind of pumped their brakes. So I would say don't know the speed and times between the given ones. Don't know the time and speed between the given values. Okay? All right, moving right along. You jump out of a plane. Before your parachute opens, you are in a free fall. While your speed increases, your acceleration decreases as you fall because of air resistance. The table on the right gives acceleration, A, in meters per second for the first 6 seconds If time is measured on the x-axis and A is measured on the y-axis, find the area under the curve using a trapezoidal rule with 6 trapezoids and a midpoint Riemann sum with 3 rectangles, and interpret the area using correct units. Okay? All right. So let's go to trapezoid. So trapezoid, we know, so we're using 6 trapezoid. Luckily for us, there's 6 of those, okay? So trapezoid rule is base over 2. So our base is just 1 here, so we say b over 2 is 1 over 2. So 1/2, okay? And then the first one, okay, you just say f of 0. Remember, we're going to use them all, so this would be f of 0, f of 1, f of 2, f of 3, yada, yada, yada. But with trapezoid, you got to say f of 0. And I'm actually just going to put these numbers in instead of writing the formula. So f of 0 is 9.81. Plus, remember here you got to say 2f of 1. So you got to multiply f of 1 times 2. And I've done that calculation and I get 16.06. Plus 2f of 2 would be 13.06. And again, that's just doubling each one of these. We're going to double it. We don't double the ends. 13.06 plus 10.76 plus 8.82. And then I'm going to come down here plus 7.22. That would be double 3.61 and then plus 2.78. Again, we don't double the beginning and the end. We just double everything between. And again, that's the reason we're doubling that is because it's basically the average of the left and the right. So using all of it, but doubling the 2. Okay? And then we should find our area. If we were to use a calculator, we would get 34.255 meters per second. Now, to do the midpoint Riemann sum, and here we would have, how many rectangles did it say? 3 rectangles? Okay. So, notice here that if we have 3 rectangles, our base would be 2. Okay, now let's flip back over and see the midpoint. It's the base times x0 to x1 divided by 2. Okay, from x0 to x1 divided by 2, and then you just keep adding them. So our midpoint Riemann sum here, the area is approximately 2, which is our base here, if we have 3 rectangles. Okay? So, this is actually going to be pretty simple within it, okay? Because think about this. There's 3 rectangles, and we're calculating the midpoint of each. So from 0 to 2 would be 1 rectangle, right? It has a base of 2. You with me on that? Then from 2, I know this is going to look a little confusing, but hopefully you see it. And then from 2 to from 2 to 4 would be the next one. Man, I butchered that. Sorry, guys. And then from this point to that point. Yeah, so I butchered that. So that I'm sure that makes 0 sense now. Okay? But basically, what I was trying to show you was with each one of these, okay? With each one of these, it's just basically going to be the middle point, okay? If you have 3, if each one has 3, if there's 3 rectangles, well, remember back here where we said that midpoint would just be calculating you're just calculating what's between the bases, 1.5, 2.5, 3.5. So really, we're just calculating here what's between each base. So we're just calculating 1, 3, and 5. So here we just got to say 8.03 plus 5.38 plus 3.61. Okay, it's just kind of the middle of those. So with midpoint, when you're given two things, it's just going to be whatever the middle f of 1 would be. So f of 1 here is 8.03. So this would just be f of 1. This is the middle of it. F of 3 and f of 5. And from that, you would get the area is approximately 34.04. So most of the time it's kind of messy, but one like that, it kind of works out pretty good for you to do that. And the reason it's meters per second is because the second and the second squared would cancel out, leaving just meters per second. So this is their approximate speed. If we were to interpret it, this is the approximate speed after what? 6 seconds? Yeah. Okay. All right, so that's trapezoidal and midpoint. Luckily, that midpoint kind of worked out where there's perfect points right between each rectangle. Sorry, I butchered the drawing of the rectangle. I thought I could do something unique there, but it kind of looked messy there. Okay. Actually, I can't live it up just because I feel like I let you down. So I want you to think if this was between 0 and 2, 0, 1, 2, and 3 and 4. That's 3. Oh no, sorry. 0, 1, 2, 3, 4, 5, and 6. There would be 3 rectangles going up, okay? And of course, I don't know what the curve looks like, but I'm just trying to get you to see the point here in this. Is that, and then your midpoint would just be right there, which is f of 1, f of 3, f of 4. Okay, just trying to kind of show you that. All right, sorry about that. I thought I could do it on a table, but it looks too sloppy. All right, last page, guys. Be happy. Almost 2 hours in lecture. I appreciate you guys staying with me. These last 3 shouldn't be bad because I hope we're kind of getting the hang of it. They are going to be a little bit different. So when intervals are not the same, you need to create individual rectangles or trapezoid when computing area. So I'm going to star that. So when your intervals or your bases are not the same, you have to create individual rectangles or trapezoids when you're computing the area, okay? Which is not bad, okay? It's not bad. It's just when those bases are not like when each base is not like 1, 2, 3, 4, 5. When it's like 1, 7, 18. When the bases are different, you just need to calculate the area of each trapezoid, then go to the next one, okay? You'll kind of see what I'm talking about here on this last page. So, over a period of an hour, vehicles are lining up to go over a bridge. The table to the right shows the rate that vehicles join the line. Use the trapezoid rule to approximate the number of cars that have lined up in the hour. So, starting with our vehicles, okay? So, we got vehicles here. Now, notice, this is what I'm talking about. Notice that from 0 to 10, and then 10 to 25, and then 25 to 40, then to 45, then to 60. The bases are not going to be the same. Your intervals are not they're not going up at the same rate. So when that's the case, you have to create basically a rectangle or a trapezoid for each one, okay? So we're going to create a trapezoid from 0 to 10. Then we'll create a trapezoid from 10 to 25. And then one from 25 to 40. And then one from 40 to 45, 45 to 60. Okay? So the work's probably going to look like a lot, but it's really not that bad. All right. So here we go. Your vehicles would be equal to, again, keep in mind that the formula for the trapezoid area would be, it starts with 1/2 times the base. 1/2, and the base here on this first one from 0 to 10 would be 10. So 1/2 times 10, and then times, okay, f of 0 and f of 10. And we add those two together. So 20 and 25. I'm going to show you on this one. So like 20 plus 25. That would be like f of 0, f of 10. Okay, we put them together. And then we add that to the next one. So 1/2 times, from 10 to 25, our base would be 15. And if you saw this on a graph, you could see, like with the intervals not being the same, that some trapezoids are going to be, the base is going to be big, sometimes it's going to be small. So with it being, with them not being the same, we just have to calculate each area separately, okay? So 1/2, 15 is the base here, and then it's 25 plus 45. Then we go to the next one. 1/2 times 15, 25 to 40 is 15, and then 45 and 50. 45 plus 50. And then plus 1/2. That next distance is only 5, and we go from 50 to 70. So 50 plus, not 70, I said the answer, 50 plus 20. And then the last one would be plus 1/2 times 15, and then 45, or excuse me, 20 and 15. So then here's just some pretty basic math, guys. So that would be 225 plus 525 plus 712.5 plus 175 plus 262.5, and that would give us a total of 1,900 vehicles. So it wanted to know how many cars lined up in an hour. 1,900. All right, so those vehicles are starting to line up to go over a bridge. How many came in an hour based on these numbers? 1,900. And that you're just literally finding the area under this right here. Finding the area of each trapezoid. All right, moving on. Hope you guys are good on that. Number 7, just 2 more problems. A swimming pool containing 63,000 gallons of water is too cold, so the pool drains water while pumping in warmer water. The table below shows the rate that water is pumped in and the rate the pool drains in gallons per minute at various times over a 12-hour period. Using the trapezoid rule, how many gallons of water are in the pool at the end of the 12-hour period? Okay, so we got basically 2 factors here, water in and water out. So water in. All right, so let's talk about water in. So, again, trapezoid, we're going to use 1/2, okay? And unfortunately, since that goes up by 2, that goes by 3, that goes by 3, that goes by 2, that goes by 2, we can't just put it all together. We have to calculate individual trapezoid areas. So water in, we say, is 1/2, all right? So 1/2 times the first distance between the two, which would be 2. 1/2 times 2. And then this is the water pumped in. So the 300 plus 200, and instead of putting the add sign, I'm just going to put 500 this time. I'm just going to put it what it is, save me some room. And then plus 1/2 times the distance between 2 and 5 is 3. And 200 and 300 is 500. And then plus the distance between 5 and 8 is 3. And then 300 and 400 is 700. Plus the distance between 8 and 10 is 2. 1/2 times 2. And then 400 and 200 is 600. And then the last one, the distance between 10 and 12 is 2. And then I multiply that times 300. If you were to add all of that up, you would get a total of 3,200. I'm kind of saving us the calculator time. So then we go water out. Water out would be this. 1/2. The first is 2. All those are going to be the same, but the numbers will be a little bit different. 600 plus 1/2 times 3 would be 500 plus 1/2 times 3 would be 400 plus 1/2 times 2 would be 350. And then plus 1/2 times 2 would be 250. Okay, so when you do all that math, if you were to type that in your calculator, it'd actually be pretty simple in your head even as well. But that would be 2,550. All right. So the water in the pool currently is 63,000. When we add 3,200 to that, when we add 3,200 and take away 2,550, or we just take that and then subtract that from 6,300, or add it, whatever it be, you would get 63,650. Not sure if you guys are still with me. You guys still with me? Hadn't talked to you in a couple, about 20 minutes. You guys still with me there? Give me a thumbs up if this is making a little bit of sense to you. Cool, Morgan. Thanks for hanging on with me. One more problem. All right, cool. Are you guys, all right, one more problem. I know your brain is probably fried. A lot to take in. This is a huge lesson. And you guys know that anytime if you need to go, you could, and just come back later and watch it if your brain's too fried. Last one, though. At 5 p.m., a subway train leaves the station with 20 people still on the platform. Having just missed the train, let P of t represent the number of people on the platform at time t. At time t, waiting for the next train, which will arrive at 5:05 p.m. Values of pt are shown for every minute in the chart to the right, where t represents the number of minutes after 5. A. Examine the graph below. Find the left Riemann sum and describe the units in which it is measured. B. Confirm the second graph has the same area using Riemann sum and describe the meaning of Riemann sum. Okay. So first thing we need to do is come down here to A, and it says examine the graph below, find the left Riemann sum, and describe the units in which it is measured. Okay, so A. So the left Riemann sum says this: take all your left points and don't worry about the far right one. Okay, so and our base is the same. It's just 1 minute, 2 minute, 3 minute, 4 minute, 5 minute. So our base is just simply 1. And then we just need to simply add that with all of these areas. Now, it's very conveniently up here in this table for us. So we just need to say 1 times the first one, which is 20. That gives us that area. And then plus, since the bases are all 1, guys, we can just say 1 times the sum of all of these. So 20 plus 50 plus 80 plus 100, and I'm getting them from up here, so I don't want you to think that I'm looking at that map or the graph that fast. Plus 140, and I don't include 160 because that's the right handmost point. And from there, I get area is equal to 390 people, and that is per, and that's like people a minute. It's kind of confusing. I think that's why it asks us, what does that people a minute mean? Okay. So let's go back to that people a minute. Let's go to the B part of it. Confirm the second graph has the same area using the Riemann sum and describe the meaning of the Riemann sum. So for this right here, the area, so notice this rectangle right here. It's a 5 by 20. A 5, notice this rectangle, it's width of 5 and a length of 20. Because that's that same point over there. So that to find the area, just 5 times 20, and then go to the next one, which would be a 4 by 30. 20 to 50 is 30. 4 to 30. And then a 3 by 20. No, 30 from 50 to 80. And then a 2 by, this one right here, a 2 by 20. And then a 1 by 40, plus a 1 by 40, since that goes up to 140. So this just kind of confirms that. And again, that gives that whole 390, if you were to add all that up, people a minute. Now it says that, it says, let P of T represent the number of people on the platform at T time waiting for the next train. Values of P of T are shown for every minute in the chart. Okay, so what this is saying is the figure represents the approximate total number of minutes people waited for a train. Okay, so the graph represents the approximate total number of minutes people waited for the train. You want to say hello, Linda Grace? Okay, so basically here's how that breaks down, guys. 20 people waited for 5 minutes. So this whole 300 people to minutes, the way that breaks down is it's just basically this. Right here, 5 minutes passed and 20 people waited. So 20 people waited 5 minutes. The train left at 5 o'clock and there's 20 people on the platform. So that means that the next train didn't arrive till 5:05, so there's 20 people on the platform. So 20 people waited waited the whole 5 minutes for the next train. Well, then that would mean 30 people, which is the next distance up, right? They waited 4 minutes. And then the next distance up would be another 30 people. 30 other people waited 3 minutes. And then 20 up from there, 20 people waited 2 minutes. And then 40 people waited 1 minute. And then the remainder of those, the last 20 people, okay? So again, these 20 people waited 5 minutes for the train. There's an additional 30 more, so they waited 4 minutes. There was an additional 30 more, so they waited 3 minutes. There was an additional 20, so they waited 20. There was an additional 40, so they waited 1 minute. And these additional 20 that showed up at 5:05, the additional 20 didn't wait at all. The last 20 didn't wait at all. Do you all love calculus or what? Y'all feel okay about this? What do y'all think? Insane, stupid, goofy? This is pretty straightforward, pretty easy. What do y'all think? Carter said not too bad. Cool. A lot, but straightforward. Yeah, it is a lot. It's a lot today. Luckily for you all, yeah, that is true. You got to set the formula up correct, and with practice, it'll get you there, okay? And this is where that practice is really going to come in hand, guys. So now, look, your homework is literally 1 page. That's pretty insane. But for each problem, right here, A, B, C, and D, approximate the area under the given function using the specific numbers of rectangles or trapezoids. For trapezoids, use Trapezoid Rule and confirm the answer is the average of LRS and RSS. Answers are given to so you know what you are doing, know that you're doing the problem correctly. So look, already giving you the answers for all of these, okay? All the answers are in here. What you need to do is go this function right here. You need to, based on this right here, you need to go show all your work for LRS, RRS, midpoint, and the trapezoid. Show all that work, okay, on a separate sheet of paper. I will be looking for 29 homework to be on a separate sheet of paper when I collect this. You basically have, today is Thursday, you have Friday, Saturday, Sunday, Monday. You have 5 days, guys, and the rest are just one-word problems, so they're not too bad, okay? So just wanted you to be aware of that. Make sure you do A, B, C, and D. All of this work. This is just to confirm your answer on a separate sheet of paper. And then you're good here, good in here. You should be able to work these out here. If you guys have any questions, shoot them to me right now, or you can email me. If you don't have any other questions of me, you guys are free to go. Thanks for hanging on for so long. It's 2 minutes, or 2 hours. I wish it was 2 minutes. 2 hours and 15 minutes. You guys did extremely well. Thanks for hanging on. And I know that's a lot to take in at one point. Feel free to go back and watch it at a different time if you're like just zoning out at some point. I just had to get it done with us being online, so that's why I had to go so long. I would prefer to break it up, but it is what it is. Yes, Morgan, we are doing Zoom at 8. If you guys want to do that, we'll see who all will show up at 8 o'clock, all right? Rocket. If you guys don't have anything else, I'll see you at 8 o'clock tonight on Zoom, or I'll see you next Tuesday. You guys have a good day.